Hello everyone. In this video we'll be talking about how to calculate the pH of a weak acid. So here we have a pretty typical question. It says calculate the pH of a 2.00 molar solution of nitrous acid. The Ka for this nitrous acid is 4.5 times 10 to the negative fourth. Alright, first things first, you need to know that this is a weak acid. If you don't know that this is a weak acid, go back and find a list of the strong acids and start memorizing them. That's the best advice I can give. But we have a weak acid in water. So let's go to where my brain immediately goes. I have a go-to steps for how to determine the pH of a weak acid when given these two bits of information. That's a pretty vanilla version of this problem, so we're just going off of it. Now, the point of any acid pH problem is to figure out the H3O plus or the hydronium concentration. Unfortunately for us, weak acid involves an ice table to get there. So you can't just pop straight to H3O plus concentration like you can do with a strong acid. So I like to remind my students, because this is where they usually get stuck at the very beginning, let's write out a chemical reaction. So when you have nitrous acid in a bucket of water, it'll undergo one, equilibrium. That's important. That's different from a strong thing, a strong electrolyte. But also it'll undergo the Bronsted-Lowry donation of a proton. So this proton right here is going to split off and get donated to the water. So the water is acting as a base in this problem. You're left with the conjugate base and hydronium. This is super duper typical of weak acids. You're left with a conjugate base and hydronium. But it's our job to figure out the concentration of hydronium at the end. So my whole goal is to figure that out right there. Now with the heterogeneous mixture, you know that you can cross out your pure liquid waters. In this problem, we start with 2.00 molars of the reactant and 0 products. Unless there's a common ion effect going on, you can start off with 0 products. And hopefully you're familiar with the idea of ice tables, where we'd fill out the rest of this ice table looking like this. Wonderful. Now, after every ice table, again, our long-term goal is to figure out what X is, but after every ice table, I like to remind myself and go with the equilibrium expression. For an acid, we have Ka is equal to the products over the reactants. Remember, don't include pure solids or liquids in equilibrium expressions. Now, in this problem, we're given all those numbers or algebraic expressions. We have 4.5 times 10 to the negative fourth is equal to x squared over 2.00 minus x. Now, if you're using the quadratic equation, either with a numeric solver from your calculator or by hand with the quadratic equation, you can definitely figure out what x is. But there's a rule of thumb that you can use to approximate x, and it makes your life a lot easier. If the initial concentration of the acid, or the thing that's dissociating, is greater than 100 times the Ka, then any difference of x is insignificant, and all of a sudden we don't have to use the quadratic equation. What we would do, is multiply the 2 by both sides, take the square root, and I'm just going to do that on my calculator really quickly. 4.5 times 10 to the negative fourth times 2 square root. I get that x is equal to 0.03 molar. Why is that important? Because the ice table tells us that x is equal to H3O plus. Wonderful. We are now done with the ice table and got what we need. I like to tell my students we are now in the top left corner of the rectangle. We're at H3O plus. We just need to get down to pH and we'll be done. There's a formula for that. Depending on what school you go to or what class you're in, that may be given, may not be given, where pH will be equal to the negative log of hydronium concentration. I'm going to zoom in on that. So pH should equal negative log of 0.03. And when I plug that into my calculator, negative log of 0.03, I get a pH of 1.52. That's my final answer. And as always, think. Did we have an acid or a base at the beginning of this problem? And according to the beginning of the problem, we had an acid. So what do you know about acidic pHs? Are they greater than 7? Less than 7? Less than 7. So this makes sense. It's a pretty intense weak acid, but that's okay. The math all worked out, and that's what we got. Hopefully this question is helpful, and reach out if you have any questions about it. Thank you.